Picture this: a mountain-sized chunk of ancient ice and rock, born around a star we've never seen, racing toward our sun at speeds that would cross the United States in 3 minutes. This isn't science fiction. This is 3I Atlas, humanity's third confirmed visitor from interstellar space. And it might be about to do something that could fundamentally change how we understand both cosmic wanderers and our own solar system's delicate balance. Right now, as you listen to these words, this enigmatic traveler is approaching the most dangerous phase of its billion-year journey. In just weeks, it will dive closer to our sun than Mars ever ventures, entering a region where temperatures soar and magnetic fields dance with deadly precision. But here's what makes your spine tingle. This isn't just any comet making a routine solar flyby. 3I Atlas carries secrets that challenge everything we thought we knew about objects from the space between stars. What if I told you that this visitor might possess the power to trigger cascading effects throughout our solar system? What if its unusual chemistry, its impossible mass, and its perfectly timed arrival aren't just coincidences, but pieces of a cosmic puzzle that could reshape our understanding of how the universe works? Tonight, we're going to explore a possibility that keeps astronomers awake, stare at data that doesn't quite fit the models they've spent lifetimes building. Welcome to a journey through one of the most perplexing astronomical discoveries of our time. I'm your guide through this cosmic mystery, and over the next hour, we'll dive deep into the strange case of 3I Atlas. We'll examine why this object has scientists questioning fundamental assumptions about interstellar visitors. We'll explore the mounting evidence that suggests this cosmic wanderer might be capable of influencing our sun in ways we're only beginning to understand. And we'll investigate whether humanity is about to witness something unprecedented in recorded history. But first, let me share something that will change how you think about our place in the cosmic neighborhood. The space between stars isn't empty. It's a vast ocean filled with wandering objects, debris from planetary systems that formed when our galaxy was young and chaotic. Most of these travelers remain invisible, dark and cold, drifting for millions of years without ever encountering another star. But occasionally, one of these ancient voyagers finds its way into our solar system, carrying with it chemical signatures and physical properties that tell stories of alien worlds we can never visit directly. 3I Atlas is only the third such visitor we've ever confirmed, but it's already proving to be the most enigmatic. Discovered on July 1st, 2025, by the Atlas Survey Telescope in Chile, this object immediately stood out as something unusual. Its trajectory marked it as definitively interstellar, unbound by our sun's gravitational influence, following a hyperbolic path that will carry it back into the cosmic dark after its brief passage through our neighborhood. Within weeks of discovery, something remarkable began happening. Telescopes around the world swung into coordinated action, creating the most comprehensive observation campaign ever mounted for an interstellar visitor. The Hubble Space Telescope interrupted its scheduled observations to capture detailed images. The James Webb Space Telescope dedicated precious time to analyzing the object's chemical composition. Ground-based observatories from Chile's Atacama Desert to Hawaii's volcanic peaks contributed observations across the electromagnetic spectrum. What they found challenged expectations at every turn. Instead of the familiar behavior exhibited by previous interstellar visitors, 3I Atlas began displaying characteristics that didn't fit established patterns. It developed an unusual forward-pointing glow, creating a sunward tail that seemed to defy basic physics. Its chemical composition revealed unprecedented ratios of carbon dioxide to water, suggesting formation in environments far colder than typical comet birth regions. Most puzzling of all, spectroscopic analysis detected nickel emissions without corresponding iron signals, a chemical asymmetry that has theorists scrambling for explanations. But these anomalies pale in comparison to the discovery that has researchers questioning their fundamental understanding of interstellar objects. Through precise measurements involving over 4,000 individual position observations From more than 200 observatories worldwide, astronomers determined that 3I Atlas might weigh at least 33 billion tons. To put that in perspective, this cosmic visitor could outweigh the Empire State Building by a factor of 40,000. How is such massive weight possible for an object showing active comet behavior? Traditional physics suggests that gas escaping from a comet's surface should create tiny, rocket-like forces that nudge the object off its gravitational trajectory. These non-gravitational accelerators of comets throughout aeons have been observed in hundreds of our solar system. They're as predictable as sunrise, fundamental signatures of how ice transforms to gas under solar heating. Yet 3I Atlas shows virtually no such acceleration despite clear evidence of active outgassing. Water vapor streams away from its nucleus at hundreds of meters per second. Carbon dioxide creates an extended atmosphere, reaching hundreds of thousands of kilometers from the solid core. The object breathes like a comet, develops a coma like a comet, exhibits spectroscopic signatures exactly like a comet, but it refuses to be pushed around by its own exhalations like a mountain ignoring morning mist. This disconnect between visible activity and missing orbital perturbations forces an uncomfortable conclusion. Either our understanding of comet physics is fundamentally incomplete, or 3I Atlas possesses mass far exceeding anything we've encountered in previous interstellar visitors. The implications of either possibility extend far beyond academic astronomy into questions about the nature of matter itself and how it behaves in the extreme environments of interstellar space. Consider the journey this object has undertaken to reach our solar system. If current age estimates prove correct, 3I Atlas has been wandering the galaxy for billions of years, potentially since before our Sun ignited nuclear fusion. During this incomprehensible voyage, it has witnessed the birth and death of countless stars, survived passage through interstellar radiation fields that would sterilize any known form of life, and endured temperature fluctuations that cycle between the absolute cold of deep space and the searing heat of chance encounters with distant suns. What kind of object survives such an odyssey intact? What processes could create something so massive yet so chemically active? The answers may lie in understanding formation environments unlike anything in our local solar neighborhood. If 3I Atlas originated in the outer regions of a stellar system much different from our own, around a star with different mass, temperature, or chemical composition, it might have condensed from materials and under conditions that our current theories struggle to accommodate. The carbon dioxide dominance detected by Webb's infrared spectrograph tells part of this alien origin story. This chemical signature suggests formation beyond what astronomers call the carbon dioxide snowline, regions so cold that carbon dioxide freezes solid alongside water ice. In our solar system, such conditions exist only in the frigid outer reaches beyond Neptune's orbit. But around different types of stars, these snowlines might extend much closer or much farther from the central fire, creating formation environments that produce objects with chemical compositions unlike anything we've studied before. The nickel emissions present another piece of this cosmic puzzle. Seeing abundant nickel spectral lines without corresponding iron features resembles finding a forest full of oak trees, but no maples in regions where both species normally coexist. In typical astronomical environments, these metals appear together because they form through similar nuclear processes and often exist in comparable chemical compounds. The selective appearance of nickel suggests either exotic formation conditions or unusual chemical processing that preferentially liberates one metal while keeping the other bound in solid form. These chemical anomalies might indicate that 3I Atlas formed in environments where different physical processes operated, perhaps around stars with unusual compositions, or in regions of space where cosmic radiation, magnetic fields, or other factors created conditions unlike those we observe in our local galactic neighborhood. Understanding these alien formation environments could provide insights into stellar evolution, planetary system development, and chemical processing operating throughout cosmic history. But chemistry represents only one aspect of the mystery surrounding this interstellar wanderer. Its approach trajectory raises equally perplexing questions about cosmic coincidence and statistical probability. 3I Atlas approaches our solar system along a path nearly aligned with the planetary plane, tilted by only 4 degrees from the ecliptic. Such precise alignment occurs randomly in roughly 1 case out of 500 for objects arriving from arbitrary interstellar directions. While not impossible, this geometric precision raises questions about whether we're witnessing natural orbital mechanics or something more purposeful. The trajectory also creates a series of planetary encounters that reads like a carefully planned reconnaissance mission. The object passes within range of Mars in early October, reaches closest approach to the Sun in late October, then continues outward for a close encounter with Jupiter in March 2026. Each encounter offers unique observation opportunities, while testing the object's response to different gravitational and radiation environments. The timing of these encounters creates both opportunities and challenges for astronomical observation. The Mars passage occurs at a distance that places the object within potential range of spacecraft currently orbiting the red planet. European and American missions, including Mars Express, the ExoMars Trace Gas Orbiter, and NASA's MAVEN, could theoretically observe 3I Atlas from vantage points impossible to achieve from Earth-based telescopes. Such multi-perspective observations would provide unprecedented insights into the object's true nature, revealing details about its surface properties, coma structure, and activity patterns that remain hidden when viewed from a single location. The different viewing geometries available from Mars' orbital positions could resolve questions about the unusual sunward glow and help distinguish between various theoretical explanations for the object's anomalous characteristics. The Jupiter encounter presents even more intriguing possibilities, including proposals for redirecting NASA's Juno spacecraft toward an intercept trajectory with 3I Atlas. Multiple research teams have outlined technically challenging but potentially feasible mission concepts that would provide humanity's first close-up examination of an interstellar visitor. Such encounters could revolutionize our understanding of these cosmic wanderers by providing direct measurements of composition, structure, and behavior impossible to achieve through remote observation alone. The gravitational mechanics required for such a Juno redirection would push spacecraft engineering to its absolute limits. The mission would demand what aerospace engineers call gravity assist maneuvers, using Jupiter's immense gravitational field to amplify the effectiveness of the spacecraft's limited fuel reserves. By firing engines at the precise moment of closest approach to Jupiter, where orbital velocities reach their maximum, each drop of propellant could provide maximum momentum change for trajectory modification. Congressional representatives have already sent letters to NASA urging detailed study of repurposing Juno for this unprecedented interstellar investigation. The political attention underscores extraordinary public fascination with 3I Atlas, while reflecting growing recognition that such opportunities may not arise again for decades. The scientific payoff from successful close encounter would dwarf anything achievable through remote observations, potentially providing direct analysis of dust composition, grain size distributions, isotopic ratios, and magnetic properties. Yet the fuel limitations present the primary technical constraint. Juno was never designed for major trajectory changes and carries only limited propellant reserves for orbital adjustments around Jupiter. Reaching 3I Atlas would require expenditure of essentially all remaining fuel, permanently ending any possibility of returning to Jupiter science operations. The decision represents a classic trade-off between guaranteed known science and potentially revolutionary unknown discoveries. But why should this particular interstellar visitor capture such intense scientific attention? The answer lies in understanding what 3I Atlas might reveal about processes operating throughout our galaxy. Every wandering object that enters our solar system carries information about conditions in stellar environments we can never visit directly. Chemical compositions, isotopic ratios, and physical properties preserve records of formation processes that occurred around different stars during various epochs of galactic evolution. 3I Atlas appears to sample conditions quite different from our local stellar neighborhood. Its unusual chemistry suggests formation around stars with different masses, temperatures, or evolutionary histories than our Sun. The carbon dioxide enrichment points toward birth in extremely cold environments, possibly around low-mass stars where habitable zones extend much closer to the central fire, pushing ice formation regions to greater distances than we observe in our own system. The temporal dimension adds another layer of cosmic significance. If age estimates prove correct, 3I Atlas has been wandering space for billions of years, potentially carrying chemical memories from when our galaxy was young and chaotic. During its journey, entire generations of stars have been born, lived full stellar lifetimes, and died in supernova explosions that seeded space with heavy elements. This ancient traveler witnessed cosmic evolution spanning geological timescales that dwarf human comprehension. Understanding objects like 3I Atlas provides windows into galactic history otherwise impossible to access. While we can study distant stars through their light and infer properties through spectroscopy, interstellar visitors carry actual physical samples of materials that formed around those distant suns eons ago. It represents cosmic archaeology, allowing direct examination of matter processed in environments billions of years in the past. The population statistics surrounding interstellar visitors raise equally profound questions about the nature of debris wandering between stellar systems. Current theoretical models predict that smaller objects should vastly outnumber larger specimens in the interstellar medium. Ejection from planetary systems typically favors less massive debris because smaller objects require less energy to accelerate to escape velocity. Detection biases should further favor smaller objects within certain size ranges. Yet, our sample of confirmed interstellar visitors defies these statistical expectations. Oumuamua, our first detected wanderer, showed unusual properties, including anomalous acceleration without visible outgassing. 2I Boris behaved like a conventional solar system comet, reassuring in its familiarity. Now 3I Atlas introduces characteristics that strain conventional explanations, potentially representing the most massive specimen by orders of magnitude. This progression from unusual to normal to potentially revolutionary suggests either that our understanding of interstellar debris populations requires fundamental revision, or that we're witnessing statistical fluctuations in an extremely small sample size. With only 3 confirmed examples, drawing broad conclusions about population characteristics approaches meaninglessness. Early data fluctuations commonly produce misleading impressions that resolve as sample sizes increase. The Vera Rubin Observatory promises to revolutionize our understanding by detecting hundreds or thousands of interstellar objects over the next decade. This statistical revolution will transform speculation based on individual examples into robust empirical science, capable of testing theoretical predictions about size distributions, chemical diversity, and orbital characteristics. But until these future discoveries provide clarity, 3I Atlas stands as a puzzling ambassador from the space between stars. Its anomalous properties, whether real or apparent, serve as prompts for better observations, improved theoretical models, and deeper questions about cosmic processes operating on galactic scales. The uncomfortable implications force examination of fundamental assumptions about how matter moves through the universe. The chemical mysteries surrounding this visitor extend beyond simple compositional analysis into questions about survival mechanisms operating during interstellar transit. Objects traveling between stellar systems face environments hostile to complex chemistry. Cosmic radiation gradually destroys molecular structures over million-year timescales. Temperature cycling between the absolute cold of deep space and heating from chance stellar encounters creates thermal stress that can shatter brittle materials. Yet 3I Atlas has not only survived its billion-year journey, but retained chemical signatures complex enough to puzzle contemporary spectroscopists. The preservation of volatile compounds like water ice, carbon dioxide, and exotic organic molecules suggests either extraordinary protection mechanisms or formation processes that created unusually robust chemical structures capable of withstanding interstellar hazards. The survival question becomes particularly acute when considering the object's apparent great age. If 3I Atlas truly originated during earlier epochs of galactic evolution, it has endured cosmic conditions quite different from those operating today. The early galaxy contained different stellar populations, different chemical abundances, and different radiation environments. Understanding how objects formed under those ancient conditions could survive transport to the present day requires sophisticated modeling of chemical and physical evolution over cosmic timescales. These considerations lead naturally to questions about what other ancient travelers might be wandering through our cosmic neighborhood undetected. Current surveys discover interstellar visitors only when they pass close enough to the Sun to develop visible comas or reflect sufficient sunlight for direct detection. The vast majority likely remain invisible unless they happen to follow trajectories that bring them within the inner solar system during periods when Earth-based telescopes can observe them. Statistical estimates suggest that our solar system encounters numerous interstellar objects annually, most passing unnoticed through the outer regions where they remain too faint for detection. The 3 confirmed visitors represent only the tip of a much larger population that includes specimens spanning wide ranges of sizes, compositions, and origins. Future surveys will reveal this hidden population, transforming our understanding of the galactic debris field. The discovery rate acceleration promises to provide answers to fundamental questions about cosmic recycling processes. Stars continuously eject material through various mechanisms, including planetary system formation, stellar winds, and explosive events. This ejected matter becomes the raw material for interstellar wanderers that eventually encounter other stellar systems. Understanding these processes illuminates how matter moves through the galaxy and what that movement reveals about cosmic evolution. 3I Atlas thus represents more than just another unusual astronomical discovery. It embodies questions about connectivity, survival, and information transfer operating across scales spanning individual molecules to entire galactic populations. Whether this particular visitor proves conventional or revolutionary, it has already succeeded in expanding our perspective about processes operating in the vast spaces between stars. The mounting evidence suggests we stand at the threshold of a new understanding about our cosmic neighborhood. The space between stars may be far more dynamic and interconnected than previously imagined, filled with ancient messengers carrying information about stellar environments and evolutionary processes spanning billions of years of galactic history. But what happens when this ancient wanderer reaches the most turbulent region of our solar system? What occurs when billions of tons of exotic matter, supercharged with unusual chemistry, plunges into the magnetic chaos surrounding our Sun? This is where our story takes a dramatic turn, because 3I Atlas isn't just passing through our neighborhood as a passive observer. It's about to enter a zone where the very fabric of space itself writhes with electromagnetic violence. The region approaching our Sun represents one of the most dynamically unstable environments in the known universe. Here, magnetic field lines stretch and snap like invisible rubber bands, releasing energy equivalent to millions of nuclear bombs in microseconds. Solar plasma, heated to temperatures exceeding those found in stellar cores, races outward at speeds that would traverse the Earth's diameter in minutes. Into this maelstrom, 3I Atlas carries something unprecedented, a chemical cocktail that could interact with our Sun's magnetic field in ways we've never witnessed before. Consider the implications of what's about to unfold. Our visitor doesn't just carry ordinary ice and rock. Its unusual composition includes metallic elements in ratios that challenge everything we understand about natural formation processes. The nickel emissions detected by Earth's most powerful telescopes represent just the beginning of a chemical inventory that might include exotic compounds formed under conditions impossible in our local solar environment. When this material begins sublimating under intense solar heating, it won't just create a typical comet tail streaming harmlessly into space. Instead, it could introduce electrically conductive particles into regions where the sun's magnetic field undergoes its most violent transitions. Imagine dropping metal filings into a transformer operating at maximum capacity. The results could cascade through the entire solar system in ways that make current space weather predictions obsolete. The timing couldn't be more significant. 3I Atlas approaches perihelion during a period when our sun's magnetic activity cycle nears its maximum intensity. Solar maximum brings increased sunspot activity, more frequent coronal mass ejections, and heightened sensitivity to any external influences that might disrupt the delicate balance of electromagnetic forces. It's like introducing a wild card into an already chaotic system. Solar physicists have spent decades studying how our star's magnetic field behaves under normal conditions. They understand the 11-year cycle that governs sunspot formation. They can predict when coronal mass ejections might threaten Earth's technological infrastructure. But they've never observed what happens when exotic acts with these interstellar matter interprocesses. 3I Atlas represents humanity's first opportunity to witness such an encounter. The potential mechanisms for interaction stretch the boundaries of current plasma physics understanding. As the comet's nucleus heats under intense solar radiation, exotic metallic compounds could sublimate into charged particles that follow magnetic field lines, like invisible highways. These particles might accumulate in regions where field lines converge, creating localized disturbances that propagate throughout the heliosphere. Alternatively, the unusual chemistry could catalyze reactions in the solar wind plasma that don't occur under normal conditions. The solar wind carries more than just protons and electrons. It transports complex electromagnetic signatures that influence everything from aurora displays to satellite communications. Introducing foreign chemistry into this system could alter the wind's properties in subtle but far-reaching ways. The gravitational influence adds another layer of complexity to potential interactions. While 3I Atlas poses no collision threat to Earth or other planets, its massive presence could create tidal effects on the sun's outer atmospheric layers. These effects would be minuscule by terrestrial standards, but in the sensitive environment of solar plasma, even tiny perturbations can trigger avalanche-like responses. Solar tsunamis represent one possible outcome. These are massive waves of plasma that race across the sun's surface at speeds exceeding 1,000,000 kilometers per hour. Normally triggered by solar flares or coronal mass ejections, such tsunamis could theoretically be induced by gravitational or magnetic disturbances from a passing massive object. The energy released by a solar tsunami dwarfs anything in human experience, equivalent to trillions of nuclear weapons detonating simultaneously. But the most intriguing possibility involves what plasma physicists call magnetic occur when twist reconnection events. These said magnetic field lines suddenly snap back into simpler configurations, releasing tremendous amounts of stored energy. The process powers solar flares, drives coronal mass ejections, and creates the spectacular aurora displays visible from Earth's polar regions. 3I Atlas could potentially trigger such reconnection events through several mechanisms. Its metallic emissions might provide additional pathways for electrical current flow, altering the stability of magnetic field configurations. Its gravitational influence could stress field lines beyond their breaking point. Most speculatively, if the object carries any residual magnetic field from its interstellar journey, that field could interact directly with solar magnetism in ways that remain purely theoretical. The Observelian passage additional challenges surrounding perid urgency to these considerations. When 3I Atlas reaches its closest approach to the Sun, it will disappear behind our star from Earth's perspective, creating a months-long observational blackout precisely when the most dramatic interactions might occur. This cosmic timing means that any solar disturbances triggered by the comet's passage might not be immediately attributable to its presence. Ground-based solar observatories will continue monitoring our star's behavior throughout this period, but distinguishing between natural solar variability and comet-induced effects will require careful analysis of subtle signatures. The Parker Solar Probe, humanity's closest approach to our Sun, offers unique vantage points that might capture interactions invisible from Earth. Its instruments could detect changes in solar wind properties, magnetic field fluctuations, or plasma dynamics that correlate with the comet's passage. The implications extend far beyond academic solar physics into practical concerns about technological civilization's vulnerability to space weather events. Our modern world depends on satellite communications, GPS navigation, power grids, and electronic infrastructure increasingly sensitive to electromagnetic disturbances from space. A significant solar storm triggered by 3I Atlas could disrupt these systems on a global scale. Historical precedent suggests the potential severity of such disruptions. The Carrington event of 1859, the most powerful geomagnetic storm in recorded history, caused telegraph systems worldwide to fail dramatically. Telegraph operators received electric shocks, telegraph paper caught fire, and some telegraph systems continued operating even after being disconnected from their power sources, running purely on induced electrical currents from the geomagnetic disturbance. In today's interconnected world, a similar event could prove catastrophic. Satellites might suffer permanent damage from radiation exposure. Power grids could experience cascading failures as transformers overload from induced electrical currents. Communication networks might collapse as electromagnetic pulses disrupt sensitive electronics. Aviation and maritime navigation systems dependent on GPS could fail precisely when they're needed most. The economic implications alone could reach trillions of dollars in damages and lost productivity. But beyond financial concerns lies the specter of technological regression. Our civilization has become so dependent on electronic systems that their widespread failure might temporarily return large portions of the world to pre-industrial conditions. Food distribution, medical care, transportation, and basic communication all rely on infrastructure vulnerable to severe space weather events. Yet, these dire scenarios speculative. The probability remain highly spec that 3I Atlas will trigger significant solar disturbances depends on numerous factors that remain poorly understood. The object's exact chemical composition, its internal structure, the precise timing of its interactions with solar magnetic fields, and the current state of solar activity all influence potential outcomes in ways that current models cannot predict reliably. Most solar physicists maintain cautious optimism that any interactions will prove scientifically interesting rather than practically dangerous. They point out that the Sun regularly encounters comets without triggering global catastrophes. They emphasize that space weather prediction has improved dramatically in recent decades, providing advance warning of most significant solar storms. They note that technological systems have become increasingly hardened against electromagnetic interference. But 3I Atlas isn't just any comet. Its unusual mass, exotic chemistry, and mysterious origins place it outside the experience base that informs current solar physics models. The interaction between interstellar matter and solar magnetism represents uncharted territory, where theoretical predictions must be tested against observational reality. The scientific community prepares for this test with mixture of excitement and apprehension. Research teams worldwide have coordinated observation campaigns designed to capture every aspect of the comet's solar encounter. Space-based telescopes, ground-based solar observatories, particle detectors, and magnetometers stand ready to record whatever unfolds during perihelion passage. The data collected during this campaign could revolutionize understanding of solar-interstellar interactions while providing crucial insights into the nature of 3I Atlas itself. If significant disturbances occur, They will offer unprecedented opportunities to study how exotic matter influences stellar magnetism. If the passage proves uneventful, it will still provide valuable constraints on theoretical models while demonstrating the resilience of solar system dynamics. The broader cosmic perspective reveals that such interactions occur routinely throughout the galaxy as interstellar objects encounter various stellar systems. What makes this event special is humanity's unique position as technological observers capable of documenting the process in exquisite detail. We stand at the intersection of cosmic-scale phenomena and human-scale consequences, witness to processes that have operated for billions of years, but never before been observed so carefully. 3i Atlas thus represents more than just another astronomical discovery. It embodies our species' growing ability to perceive and potentially predict cosmic events that affect our technological civilization. The lessons learned from this encounter will inform future preparations for similar events, helping humanity become more resilient to the electromagnetic violence that periodically erupts from our sun. The countdown continues as this ancient messenger approaches its appointment with solar fire. In the coming weeks, we'll discover whether 3i Atlas passes through perihelion as quietly as theoretical models predict, or whether it triggers electromagnetic cascades that remind us how fragile our technological cocoon really is in the face of cosmic forces beyond our control. Either outcome will mark a milestone in human understanding of our place in a universe where stellar systems exchange matter across vast distances, where ancient chemistry meets modern magnetism, and where the consequences of cosmic encounters can ripple through space to affect civilizations that evolved long after the original travelers began their interstellar journeys. But beneath these grand cosmic implications lies a more immediate and tangible concern that should make every person on Earth pay attention. 3i Atlas isn't just carrying exotic chemistry into our solar system's most volatile region. It's doing so during a period when our sun's behavior has become increasingly unpredictable, exhibiting magnetic field reversals and plasma eruptions that challenge decades of established solar physics. The electromagnetic symphony that governs our star's behavior operates on scales both impossibly vast and intimately personal. Every electrical device in your home, every satellite orbiting overhead, every power line carrying electricity to your neighborhood exists within the sphere of influence of solar magnetic fields that stretch far beyond the orbit of Pluto. When these fields undergo rapid changes, the effects cascade through space at the speed of light, reaching Earth in minutes and potentially disrupting the technological foundation upon which modern civilization depends. Recent solar observations have detected anomalous magnetic field configurations that don't match traditional cycle patterns. Sunspot groups have appeared in unexpected locations, displaying polarities that contradict established models of solar dynamo behavior. Coronal holes, regions where magnetic field lines extend into interplanetary space, have persisted longer than theoretical frameworks predict. These deviations suggest that our sun may a phase of magnetic complexity that exceeds anything documented during the space age. Into this already unstable environment, 3i Atlas brings elements that could act as catalysts for electromagnetic chain reactions. The metallic compounds detected in its spectral signature represent more than just scientific curiosities. They constitute electrically conductive materials that could provide new pathways for current flow within the sun's magnetosphere. When these materials sublimate under intense solar heating, they'll create clouds of charged particles with properties unlike anything naturally occurring in our solar system. The physics of plasma interactions in magnetic fields follows principles that seem almost magical to those unfamiliar with the discipline. Charged particles spiral along invisible field lines, accumulating energy as they travel toward regions of magnetic convergence. When field lines become twisted beyond their stability threshold, they snap back like cosmic rubber bands, releasing energy equivalent to billions of nuclear weapons in fractions of a second. The introduction of foreign metallic particles into this delicate system could lower the threshold for such catastrophic releases. Consider the cascade effects that might unfold as 3I Atlas approaches perihelion. The comet's unusual chemistry begins sublimating at distances where most solar system objects remain dormant. This premature activity creates an extended cloud of exotic particles that precedes the nucleus by millions of kilometers. As this cloud encounters the Sun's outer magnetic field lines, it could seed instabilities that propagate inward, growing in intensity as they approach regions of maximum magnetic energy density. The solar wind, that constant stream of charged particles flowing outward from our star, becomes the delivery mechanism for these disturbances. Under normal conditions, this wind carries the Sun's magnetic field throughout the solar system at speeds approaching 1,000 kilometers per second. But if 3I Atlas alters the wind's composition or electromagnetic properties, those changes will reach Earth's magnetosphere within days of their generation near the Sun. Earth's magnetic field, our planet's invisible shield against cosmic radiation, has shown signs of weakening in recent decades. The magnetic North Pole has begun wandering at accelerated rates, and scientists have detected growing anomalies in the South Atlantic, where the protective field has thinned dramatically. These vulnerabilities mean that our planet may be more susceptible to space weather effects than at any time in human history. The technological infrastructure we've built over the past century operates under the assumption of electromagnetic stability. Power grids rely on predictable current flows. Satellite systems depend on consistent radiation environments. Communication networks assume reliable propagation conditions. None of these systems were designed to withstand the kind of electromagnetic chaos that could result from major solar disturbances triggered by exotic interstellar chemistry. Financial markets have begun taking notice of space weather risks as insurance companies calculate potential losses from electromagnetic pulse events. Lloyd's of London estimates that a severe solar storm could cause economic damages exceeding $2 trillion, primarily through disruption of electronic systems and the cascading failures that would follow. These projections assume disturbances within the range of historical experience. But 3I Atlas introduces variables that push beyond the boundaries of conventional risk assessment. The timeline of potential impacts follows a predictable sequence that space weather experts have studied for decades. Initial electromagnetic disturbances generated near the Sun propagate outward at light speed, reaching Earth's ionosphere within 8 minutes. These early signals could disrupt high-frequency radio communications and GPS navigation systems almost immediately after their solar generation. The bulk plasma disturbances follow hours or days later, depending on the intensity and velocity of any coronal mass ejections that might be triggered. When this charged material reaches Earth's magnetosphere, it could compress our protective magnetic field and induce electrical currents in conductors spanning continental distances. Power transmission lines become giant antennas picking up electromagnetic energy from space, potentially overloading transformers and triggering cascading blackouts. Satellite systems face the most immediate and severe threats from enhanced radiation environments. The electronics aboard these spacecraft operate near their tolerance limits under normal space conditions. Increased radiation exposure could cause permanent damage to solar panels, memory systems, and communication equipment. The loss of multiple satellites simultaneously would cripple GPS navigation, weather forecasting, television broadcasting, and internet communications that rely on satellite links. Aviation presents particularly acute vulnerabilities during space weather events. Commercial aircraft flying polar routes depend on high-frequency radio communications that solar disturbances can completely disable. Navigation systems rely on GPS signals that become unreliable during geomagnetic storms. Most concerning, the increased radiation exposure at high altitudes during severe space weather events could pose health risks to flight crews and passengers on long-haul flights. The medical implications extend beyond aviation radiation exposure into broader questions about how electromagnetic disturbances might affect sensitive medical equipment. Hospitals rely on electronic monitoring systems, life support devices, and imaging equipment that could malfunction during severe electromagnetic events. Emergency services depend on communication networks vulnerable to space weather disruption precisely when they might be needed most to respond to widespread technological failures. But these practical concerns, serious as they are, represent only one dimension of the potential significance of 3I Atlas. The scientific opportunities presented by this encounter could revolutionize our understanding of fundamental processes operating throughout the universe. Never before have we possessed the observational capabilities to study how interstellar matter interacts with stellar magnetism in real time. The coordinated observation campaign preparing for perihelion passage represents the most comprehensive space weather monitoring effort ever attempted. Ground-based solar telescopes will track magnetic field changes across the Sun's surface. Space-based observatories will monitor coronal activity and solar wind properties. Particle detectors throughout the solar system will measure radiation levels and electromagnetic field fluctuations. The data collected could provide insights that reshape theoretical frameworks across multiple scientific disciplines. The Parker Solar Probe, humanity's closest approach to any star, offers unprecedented opportunities to observe 3I Atlas interactions from within the Sun's corona itself. This remarkable spacecraft operates in an environment where temperatures exceed 1 million degrees, and radiation levels would instantly destroy conventional electronics. Its specialized instruments could detect changes in solar wind composition, magnetic field structure, and plasma dynamics that correlate directly with the comet's passage. European and American missions currently orbiting Mars will provide additional vantage points during the comet's October approach to the red planet. These spacecraft could observe 3I Atlas from perspectives impossible to achieve from Earth, potentially revealing details about its coma structure, activity patterns, and electromagnetic signatures that remain hidden when viewed through terrestrial atmospheric interference. The Jupiter encounter planned for March 2026 presents even more extraordinary possibilities. Proposals for redirecting NASA's Juno spacecraft toward an intercept trajectory would provide humanity's first close-up examination of an interstellar visitor. The gravitational mechanics required for such a maneuver push spacecraft engineering to absolute limits, demanding precision navigation and fuel management that exceeds anything previously attempted in deep space exploration. The scientific instruments aboard Juno were designed to study Jupiter's magnetic field, atmospheric composition, and internal structure. But these same capabilities could revolutionize our understanding of 3I Atlas if mission planners succeed in achieving close approach. Magnetometry measurements could reveal whether the comet carries residual magnetic fields from its interstellar journey. Spectroscopic analysis could determine chemical compositions with precision impossible from remote observations. Particle detectors could analyze dust and gas directly, providing definitive answers about the object's true nature. The decision to attempt such a mission represents a classic dilemma in space exploration. Success could provide breakthrough discoveries that justify decades of theoretical work and technological development. Failure would mean the loss of valuable scientific assets and potentially years of delayed insights about Jovian system dynamics. Mission planners must weigh guaranteed known science against potentially revolutionary unknown discoveries. Congressional representatives have already expressed interest in supporting such ambitious mission concepts, recognizing that opportunities to study interstellar visitors at close range may not arise again for generations. The political support reflects growing public fascination with 3I Atlas and acknowledgement that some scientific opportunities justify extraordinary risks and resource commitments. But beyond the immediate technological challenges and scientific opportunities lies a deeper philosophical question about humanity's relationship with cosmic phenomena that operate on scales far exceeding human experience. 3I Atlas represents a messenger from stellar environments we can never visit directly, carrying information about formation processes that occurred billions of years before Earth existed. The chemical signatures preserved within this ancient wanderer provide direct samples of matter processed in alien stellar furnaces, condensed under conditions impossible in our local solar environment, and preserved through journeys spanning geological time scales. Understanding these signatures could illuminate processes of cosmic chemical evolution that shaped the galaxy long before our Sun began nuclear fusion. The isotopic ratios locked within 3I Atlas record nuclear processes that operated in stellar cores fundamentally different from our Sun. The elemental abundances reflect chemical environments where different physical laws governed matter behavior. The molecular structures preserve information about temperatures, pressures, and radiation fields that existed in regions of space we can study only through such cosmic ambassadors. Each measurement, each spectrum, each image captured during the comet's passage through our solar system adds pieces to a puzzle spanning billions of years of galactic evolution. The unusual chemistry that makes 3I Atlas so scientifically intriguing also makes it a unique archive of cosmic history, a library written in atomic structures and molecular bonds that preserve records of stellar neighborhoods we'll never visit. The population statistics surrounding interstellar visitors suggest that 3I Atlas may represent only the beginning of a new era in astronomical discovery. The Vera Rubin Observatory, currently completing commissioning phases, will scan the southern sky every few nights for the next decade, potentially detecting hundreds or thousands of similar objects. This statistical revolution will transform our understanding from speculation based on individual examples to robust empirical science. Future discoveries could reveal whether 3I Atlas represents typical interstellar visitor characteristics or remains a statistical anomaly that appeared during humanity's first systematic surveys. The answer will influence theories of planetary system formation, stellar evolution, and galactic chemical processing that extend far beyond our local cosmic neighborhood. The broader implications touch fundamental questions about connectivity and information transfer operating across cosmic scales. If interstellar objects routinely carry materials between stellar systems, the chemical evolution of the galaxy becomes a collaborative process, rather than isolated development around individual stars. Planetary systems would share common heritage through matter exchanged across vast distances and geological time periods. This perspective transforms our understanding of Earth's cosmic context from isolated development to participation in galactic-scale recycling processes. The elements composing our planet, our atmosphere, and our bodies might include materials originally formed around stars that died billions of years before our Sun ignited. Such cosmic connectivity suggests that the boundaries defining individual worlds become less meaningful when viewed from galactic perspectives. The survival mechanisms that allowed 3I Atlas to preserve complex chemistry during its interstellar journey remain poorly understood, but critically important for evaluating how information propagates through cosmic recycling networks. Objects traveling between stellar systems face environments hostile to delicate molecular structures. Cosmic radiation destroys chemical bonds. Temperature cycling creates thermal stress. Collisions with interstellar dust erode surface materials. Yet 3I Atlas has not only survived these hazards, but retained chemical signatures sophisticated enough to puzzle contemporary spectroscopists. The preservation implies either extraordinary protection mechanisms or formation processes that created unusually robust molecular architectures capable of withstanding interstellar conditions for billions of years. Understanding these preservation mechanisms could inform searches for even more exotic possibilities, including whether complex organic chemistry or potentially biological materials might survive interstellar transport. While current evidence provides no support for such speculative scenarios, the demonstrated survival of metallic compounds and volatile ices suggests that the boundaries of chemical preservation during cosmic journeys may exceed previous theoretical estimates. The temporal scales involved in 3I Atlas's journey dwarf human comprehension while providing perspective on our species' cosmic significance. If age estimates prove correct, this object began its wandering when the universe was less than half its current age. During its travels, entire stellar generations have completed life cycles, from birth through death. Planetary systems have formed, evolved, and potentially developed life countless times over. From the perspective of this ancient traveler, all of human history represents merely the final microsecond of a journey spanning cosmic ages. Our technological civilization, with its electromagnetic vulnerabilities and space weather concerns, exists within a brief moment of cosmic time, when this messenger from the deep past happens to pass through our stellar neighborhood. Yet this intersection of cosmic-scale phenomena with human-scale consequences represents something profound about our species' growing awareness of universal processes. We've developed the technological capability to detect, track, and study visitors from interstellar space, while simultaneously creating infrastructure vulnerable to the electromagnetic disturbances such visitors might trigger. The paradox captures the essence of humanity's current cosmic situation. We're sophisticated enough to perceive threats and opportunities operating on galactic scales, but still fragile enough that those same cosmic processes could disrupt the technological foundation supporting our observations. 3i Atlas thus serves as both scientific opportunity and reminder of our continued vulnerability to forces operating far beyond terrestrial control. The countdown to perihelion continues as this ancient messenger approaches its closest encounter with our Sun. Whether the passage proves scientifically revelatory or practically disruptive, it will mark a milestone in humanity's evolving relationship with cosmic phenomena that connect our local stellar environment to the broader galactic ecosystem. The data streams flowing from observatories worldwide capture not just the properties of a single interstellar visitor, but evidence of processes that have shaped matter throughout cosmic history. In studying 3i Atlas, we're examining our own cosmic heritage written in chemical signatures that predate our solar system's formation. The electromagnetic interactions that may or may not unfold during perihelion passage will provide tests of theoretical frameworks that attempt to describe how matter behaves under conditions impossible to replicate in terrestrial laboratories. The stakes extend beyond immediate practical concerns into fundamental questions about physical laws operating throughout the universe. As this cosmic drama unfolds over the coming months, humanity watches from a unique perspective, simultaneously vulnerable to the consequences and privileged to witness processes that connect our local stellar environment to the vast networks of matter and energy flowing between stars throughout our galaxy. The electromagnetic dance surrounding our Sun operates according to principles that challenge human intuition at every level. Imagine invisible rivers of charged particles flowing outward from our star at velocities that would circumnavigate Earth in 4 minutes. These streams carry plasma-embedded magnetic fields that twist and writhe like serpents made of pure energy, stretching across billions of kilometers of space before finally dissipating into the cosmic background. Within this dynamic environment, 3i Atlas now travels, carrying its cargo of exotic chemistry toward regions where temperatures soar beyond anything experienced on Earth's surface. The transition zone where the comet will soon find itself represents one of the most violent neighborhoods in our solar system, a realm where magnetic field lines stretch to their breaking point and plasma temperatures exceed those found in stellar cores. Solar physicists have spent decades mapping these invisible territories through indirect observation and theoretical modeling. They understand how magnetic field lines emerge from the Sun's interior, arch through the corona in graceful loops, then either return to the surface or stretch outward into interplanetary space. They can predict when these configurations become unstable, snapping back into simpler arrangements while releasing energy that dwarfs the combined nuclear arsenals of Earth. But their models assume interactions with familiar solar system materials. Water ice, silicate dust, and simple metallic compounds represent the standard ingredients that comets typically carry into the Sun's domain. 3i Atlas brings something unprecedented into this equation. Its unusual chemistry includes metallic ratios that don't match anything formed under conventional solar nebula conditions, suggesting origins in stellar environments operating under fundamentally different physical parameters. The nickel-rich emissions detected by ground-based spectroscopy represent just the visible portion of a chemical inventory that may include compounds unknown to terrestrial science. When these exotic materials begin sublimating under intense solar heating, they won't simply create another routine comet tail streaming harmlessly into space. Instead, they could introduce electrically active particles into regions where the sun's magnetic architecture undergoes its most dramatic transformations. The timing amplifies these concerns because 3i Atlas approaches perihelion during what solar observers call the ascending phase of solar cycle 25. This 11-year rhythm governs the sun's magnetic activity levels, driving everything from sunspot formation to the frequency of coronal mass ejections. We're currently approaching the cycle maximum, a period when our star's electromagnetic behavior becomes increasingly chaotic and unpredictable. Recent satellite observations have documented magnetic field reversals occurring at rates that exceed historical norms. Sunspot groups have appeared in unexpected locations, displaying polarities that contradict established dynamo theory. Most concerning, the sun's global magnetic field has shown signs of instability that suggest the current cycle may not follow traditional patterns. Into this already volatile situation comes an interstellar visitor carrying chemistry that could act as a catalyst for electromagnetic chain reactions. The physics of magnetic reconnection provides the theoretical framework for understanding how 3i Atlas might trigger solar disturbances. When magnetic field lines become twisted beyond their stability threshold, they undergo rapid reconfiguration events that release tremendous amounts of stored energy. These reconnection processes power solar flares, drive coronal mass ejections, and create the spectacular aurora displays visible from Earth's polar regions. Under normal circumstances, reconnection events occur when field line stress exceeds natural breaking points determined by plasma pressure and magnetic tension. But the introduction of foreign metallic particles could alter these equilibrium conditions by providing additional pathways for electrical current flow. Charged particles from the comet's sublimating nucleus might accumulate along field lines, creating localized instabilities that propagate throughout the solar magnetosphere. The cascade effects could unfold across multiple timescales and spatial dimensions. Initial disturbances generated near perihelion would propagate outward at the speed of light, potentially triggering secondary reconnection events in regions far from the comet's actual location. These electromagnetic signals would reach Earth's magnetosphere within minutes, possibly disrupting radio communications and satellite operations before the primary plasma disturbances even begin their journey through interplanetary space. The bulk material effects would follow hours or days later, depending on the velocity and intensity of any coronal mass ejections that might be triggered. When high-energy plasma clouds encounter Earth's magnetic field, they can compress our protective magnetosphere and induce electrical currents in conductors spanning continental distances. The resulting geomagnetically induced currents represent one of the most serious threats to modern technological infrastructure. Power transmission grids become particularly vulnerable during severe geomagnetic storms. The high-voltage lines American power grid could can overload and fail, triggering cascading blackouts that might Academy of Sciences estimated that a severe GE sobering projections. A studiomagnetic storm affecting the North persists for months while replacement equipment is manufactured and installed range of historical experience, but 3i primarily through the destruction of expensive transformer equipment and the cascading economic atlas introduces variables that push beyond conventional risk from disturbed space environments when induce assessment boundaries. Satellite systems face even effects of prolonged electrical, like enormous antennas, picking up electromagnetic energy outages. These calculations assume disturbances within that carry electricity across vast distances act damages exceeding $2 trillion d. The economic modelling of such scenarios produces currents exceed design tolerances, transform commissioned by the national more immediate threats from enhanced radiation environments. The electronics aboard these spacecraft operate near their tolerance limits under normal space conditions. Increased particle bombardment could cause permanent damage to solar panels, memory systems, and communication equipment. The simultaneous failure of multiple satellites would cripple GPS navigation, weather forecasting, television broadcasting, and internet communications that depend on satellite relay systems. Aviation presents particularly complex vulnerabilities during space weather events. Commercial aircraft flying polar routes depend on high-frequency radio communications that solar disturbances can completely disable. Navigation systems rely on GPS signals that become unreliable during geomagnetic storms. Most concerning, the increased radiation exposure at high altitudes during severe space weather events could pose health risks to flight crews and passengers on intercontinental flights. The medical implications extend into hospitals and healthcare facilities that depend on sensitive electronic equipment. Magnetic resonance imaging systems, computerized tomography scanners, and electronic patient monitoring devices could malfunction during electromagnetic disturbances. Emergency services rely on communication networks vulnerable to space weather disruption precisely when they might be needed most to respond to widespread technological failures. But these terrestrial concerns represent only one dimension of the unfolding cosmic drama. The scientific opportunities presented by 3I Atlas could revolutionize our understanding of fundamental processes that operate throughout the universe. Never before have we possessed the observational capabilities to study how interstellar matter interacts with stellar magnetism in real time and exquisite detail. The Parker Solar Probe stands ready to provide unprecedented close-up observations as 3I Atlas approaches perihelion. This remarkable spacecraft operates within the Sun's corona itself, protected by a heat shield that maintains instrument temperatures near room conditions, while the surrounding plasma exceeds 1 million degrees Celsius. Its specialized detectors could measure changes in solar wind composition, magnetic field fluctuations, and particle acceleration processes that correlate directly with the comet's passage. The probe's suite of instruments includes magnetometers capable of detecting field variations smaller than Earth's magnetic field, particle analyzers that can identify individual atomic species in the solar wind, and imaging systems that capture plasma dynamics invisible to ground-based telescopes. These capabilities position Parker to observe electromagnetic phenomena that might remain completely undetectable from Earth-based monitoring stations. Ground-based solar observatories worldwide have coordinated their observation schedules to provide continuous monitoring throughout the perihelion period. The Daniel K. Inouye Solar Telescope in Hawaii, the world's largest solar telescope, will capture magnetic field maps across the Sun's surface, with resolution fine enough to detect localized disturbances that might correlate with the comet's electromagnetic influence. The European Solar Orbiter mission provides additional vantage points from its elliptical trajectory that carries it closer to the Sun than any previous European space mission. Its instruments will monitor solar wind properties, energetic particle populations, and magnetic field configurations from perspectives unavailable to Earth-based observers. The combination of Parker Solar Probe and Solar Orbiter observations could provide stereo imaging of any electromagnetic disturbances triggered by 3I Atlas. Space-based X-ray and extreme ultraviolet telescopes stand ready to detect the high-energy signatures of magnetic reconnection events should they occur during perihelion passage. These wavelengths reveal the hottest plasma in the solar corona, where magnetic energy gets converted into particle acceleration and electromagnetic radiation. Any enhancement in these emissions during the comet's closest approach would provide smoking gun evidence of interaction between interstellar chemistry and solar magnetism. The Coordinated Observation Campaign represents the most comprehensive space weather monitoring effort ever attempted. Data streams from dozens of spacecraft and ground-based facilities will provide real-time coverage of electromagnetic conditions throughout the inner solar system. Advanced computer models will attempt to distinguish between natural solar variability and any disturbances that might be attributed to the comet's presence. The challenge lies in separating correlation from causation when analyzing the observational data. Solar activity follows complex patterns driven by internal dynamo processes that operate according to their own rhythms. Distinguishing between coincidental timing and genuine physical influence requires sophisticated statistical analysis of electromagnetic signatures across multiple wavelengths and measurement techniques. Theoretical models attempting to predict the outcome span a wide range of possibilities, from complete electromagnetic silence to cascading solar storms that could affect the entire heliosphere. The uncertainty reflects fundamental gaps in our understanding of how exotic interstellar chemistry behaves under the extreme conditions found near stellar surfaces. Laboratory experiments attempting to simulate these interactions face insurmountable technical challenges. No terrestrial facility can replicate the combination of magnetic field strengths, plasma temperatures, and radiation environments found in the Sun's corona. Computer simulations provide some insights, but they depend on assumptions about material properties and interaction mechanisms that remain largely untested by observation. The historical record offers little guidance because previous comets that have approached the Sun carried familiar solar system chemistry. Even the most spectacular comet encounters, such as Comet Ison's solar grazing in 2013, involved materials formed under conditions similar to those in our local stellar neighborhood. 3I Atlas represents humanity's first opportunity to observe how truly alien chemistry behaves when subjected to stellar-strength electromagnetic fields. The broader implications extend far beyond immediate space weather concerns into fundamental questions about cosmic connectivity and information transfer between stellar systems. If 3I Atlas can indeed trigger electromagnetic disturbances in our Sun, similar interactions must occur routinely throughout the galaxy as interstellar visitors encounter various stellar systems. These interactions could represent a previously unrecognized mechanism for coupling stellar magnetism across vast distances. Interstellar objects might serve as carriers of electromagnetic information, transporting magnetic field signatures and plasma properties between stellar environments separated by light years of space. Understanding these processes could illuminate aspects of galactic evolution that remain invisible through conventional astronomical observation. The chemical diversity exhibited by 3I Atlas suggests that interstellar space contains a vast library of materials formed under different stellar conditions throughout cosmic history. Each visiting object carries samples of this cosmic archive, providing direct access to matter processed in environments we can never study through traditional telescopic methods. The isotopic ratios preserved within the comet's nucleus record nuclear processes that operated in stellar cores fundamentally different from our Sun. The elemental abundances reflect chemical environments where different fusion reactions dominated energy production. The molecular structures preserve information about temperatures, pressures, and radiation fields that characterized regions of space during earlier epochs of galactic evolution. When this ancient chemistry encounters our Sun's modern magnetism, the interaction represents more than just a local space weather event. It becomes a meeting between different chapters of cosmic history, a collision between materials formed under ancient stellar conditions and electromagnetic processes operating in our contemporary solar environment. The preservation mechanisms that allowed complex chemistry to survive billion-year journeys through interstellar space remain poorly understood but critically important for evaluating the broader significance of such encounters. Objects traveling between stellar systems face environments hostile to delicate molecular structures. Cosmic radiation gradually destroys chemical bonds over geological timescales. Temperature cycling between the absolute cold of deep space and heating from stellar encounters creates thermal stress that should fragment brittle materials. Yet 3I Atlas has not only survived these hazards, but retained chemical signatures sophisticated enough to challenge contemporary understanding of interstellar object formation and evolution. The preservation implies either extraordinary protection mechanisms or molecular architectures more robust than anything found in our local. The solar system environment implications extend into speculative territory regarding what other complex materials might survive interstellar transport. While current evidence provides no support for biological preservation, the demonstrated survival of metallic compounds and exotic ice compositions suggests that the boundaries of chemical stability during cosmic journeys may exceed theoretical predictions based on solar system experience alone. The electromagnetic environment through which 3I Atlas has traveled during its billion-year journey represents another dimension of the preservation puzzle. Interstellar space contains magnetic fields, though much weaker than those found near stars. Cosmic ray particles following these field lines could have gradually modified the comet's internal structure and surface chemistry through radiation processing mechanisms. If the object carries residual magnetization from its interstellar journey, that embedded magnetic field could interact directly with solar magnetism in ways that remain purely theoretical. The collision between interstellar and solar magnetic domains might create electromagnetic phenomena without precedent in recorded astronomical observation. The rotation period and orientation of 3I Atlas during its solar encounter add geometric complexity to potential electromagnetic interactions. As the comet tumbles through space, different portions of its surface become exposed to solar heating and magnetic field lines. The resulting sublimation patterns could create asymmetric distributions of charged particles that influence how electromagnetic disturbances propagate through the surrounding plasma environment. Ground-based radar observations have attempted to measure the comet's rotation characteristics, but the results remain ambiguous due to the object's relatively small size and great distance from Earth. The rotation period appears to be several hours, but precise determination requires extended observation campaigns that span multiple rotational cycles. The surface composition mapping during perihelion passage could reveal whether different hemispheres of the nucleus carry distinct chemical signatures. If 3I Atlas formed through accretion of materials from different regions of its birth stellar system, various portions of its surface might sublimate different combinations of exotic compounds when heated by our Sun. These compositional variations could create localized electromagnetic effects that change as the comet rotates, producing time-variable disturbances in the solar wind and magnetic field environment. Such temporal modulation would provide additional signatures for distinguishing comet-induced effects from natural solar variability. The dust production patterns during solar heating present another avenue for electromagnetic interaction. As volatile ices sublimate from the nucleus surface, they carry along microscopic dust particles that become electrically charged through various mechanisms. These charged dust grains follow complex trajectories determined by electromagnetic forces, gravitational attraction, and radiation pressure from sunlight. The size distribution and composition of dust particles released by 3I Atlas could differ significantly from typical solar system comet debris. Interstellar processing mechanisms might have created grain populations with unusual optical properties, electrical conductivities, or magnetic susceptibilities that influence their behavior in the Sun's electromagnetic environment. Large dust grains follow ballistic trajectories largely unaffected by electromagnetic forces, but smaller particles become coupled to magnetic field lines and can be accelerated to high velocities by electric fields in the solar wind plasma. If 3I Atlas produces an unusually high proportion of small electrically active dust, these particles could propagate throughout the inner solar system and potentially influence space weather conditions near Earth. The interaction between comet dust and the solar wind creates phenomena visible to ground-based observers as changes in comet tail morphology and brightness. The unusual forward-pointing glow observed in early images of 3I Atlas suggests dust dynamics, unlike those seen in typical solar system comets, could provide insights into how understanding these differences interstellar materials behave under solar system conditions. The spectroscopic evolution of the comet's coma as it approaches perihelion offers real-time observations of how exotic chemistry responds to increasing solar heating. Different molecular species begin sublimating at different temperatures, creating a sequential revelation of the nucleus's chemical inventory. The unusual ratios already detected between carbon dioxide and water suggest that 3I Atlas will continue surprising observers as deeper layers of its nucleus become exposed to solar radiation. The molecular emission lines detected by ground-based telescopes represent just the most abundant species in the comet's coma. Trace scientific compounds that might be iphically significant could remain below detection thresholds until perihelion heating drives more vigorous sublimation. The James Webb Space Telescope's unprecedented infrared sensitivity could reveal molecular signatures invisible to conventional spectroscopic techniques. The spatial distribution of different chemical species within the coma provides information about their sources within the nucleus and their behavior after sublimation. Water vapor typically creates the most extended envelope around active comets, but 3I Atlas appears to show carbon dioxide dominating at much larger distances from the nucleus than typical for solar system specimens. This chemical stratification could influence electromagnetic interactions by creating regions of different electrical conductivity at various distances from the nucleus. The solar wind encounters these chemically distinct zones in sequence, potentially triggering different types of electromagnetic responses as the plasma environment adjusts to changing particle compositions and charge densities. The magnetic field measurements during perihelion passage will provide crucial tests of theoretical predictions about electromagnetic coupling between interstellar matter and stellar magnetism. If 3I Atlas carries embedded magnetic fields from its journey through interstellar space, those fields should become detectable as the comet approaches regions where solar magnetism becomes intense enough to interact with weaker external fields. The Parker Solar Probe's magnetometers represent the most sensitive instruments ever deployed in the inner solar system, capable of detecting magnetic field variations smaller than 1 part in a million of Earth's surface field strength. These measurements could reveal magnetic signatures associated with the comet that would remain completely invisible to more distant spacecraft or ground-based observatories. The coupling between magnetic fields of different origins creates phenomena that challenge theoretical understanding, even under controlled laboratory conditions. In the chaotic environment of the solar corona, where plasma temperatures exceed stellar interior conditions and magnetic field strengths approach the limits of material stability, such interactions could produce electromagnetic cascades impossible to predict through current theoretical frameworks. The energy scales involved in potential magnetic reconnection events triggered by 3I Atlas dwarf anything in human experience. A single reconnection episode can release energy equivalent to millions of nuclear weapons in microseconds, accelerating particles to significant fractions of light speed and generating electromagnetic radiation across the entire spectrum from radio waves to gamma rays. If the comet's passage triggers multiple simultaneous reconnection events throughout the Sun's magnetic architecture, the cumulative energy release could exceed anything observed during the space age. Such an electromagnetic storm would propagate throughout the solar system at light speed, potentially overwhelming the protective magnetospheres of all planets and creating radiation environments hostile to both technological systems and biological organisms. The probability of such extreme outcomes remains highly speculative. But the unprecedented nature of 3I Atlas makes risk assessment extraordinarily difficult. The combination of unusual mass, exotic chemistry, and mysterious origins places this object outside the experience base that informs current space weather prediction models. Conservative estimates suggest that any electromagnetic disturbances will likely fall within the range of natural solar variability, causing minimal disruption to technological systems while providing valuable scientific data about interstellar object interactions with stellar environments. More aggressive projections warn of cascading electromagnetic failures that could temporarily disable satellite communications, disrupt power grids, and force aviation systems to implement emergency protocols designed for extreme space weather events. The uncertainty itself has become a driver of scientific interest and public fascination. Humanity finds itself in the unique position of potentially witnessing cosmic-scale electromagnetic phenomena, while simultaneously being vulnerable to their technological consequences. The intersection of astronomical discovery with practical risk management creates tensions between scientific curiosity and prudent caution that will likely persist throughout the comet's solar encounter. The countdown to perihelion continues as observatories worldwide prepare for what could become either the most comprehensively documented comet passage in history or humanity's first direct observation of how interstellar chemistry can trigger stellar electromagnetic storms. Either outcome will mark a milestone in our species' evolving relationship with cosmic phenomena that operate on scales far exceeding terrestrial experience. The data streams that will flow from instruments throughout the solar system during the coming weeks represent more than just measurements of a single astronomical event. They capture evidence of processes that connect stellar systems across vast distances, demonstrate how matter and energy flow through galactic ecosystems, and provide tests of physical theories under conditions impossible to replicate in any terrestrial laboratory. As this ancient messenger approaches its appointment with our sun's electromagnetic fire, humanity watches from a perspective both privileged and precarious. We possess the technological sophistication to observe and potentially predict cosmic interactions, while remaining vulnerable to the very electromagnetic forces we seek to understand. The resolution of this cosmic drama will illuminate not just the nature of 3I Atlas, but fundamental aspects of how matter and magnetism behave throughout the universe. The electromagnetic symphony orchestrating our sun's behavior operates through mechanisms so complex that even our most advanced computer models struggle to capture their full dynamical range. Within this invisible architecture of magnetic field lines and plasma currents, 3I Atlas now carries its unprecedented chemical cargo toward regions where the very fabric of space-time writhes with electromagnetic violence that exceeds the combined energy output of every nuclear weapon ever constructed. Recent developments in solar observation have revealed disturbing patterns that challenge decades of established understanding about our star's magnetic cycles. The Hinode Solar Observatory has documented magnetic field configurations that don't conform to traditional theoretical frameworks. Field lines emerge from the photosphere in twisted geometries that suggest internal dynamo processes operating outside normal parameters. These anomalous structures persist far longer than models predict, creating reservoirs of magnetic energy that could discharge catastrophically under the right triggering conditions. The Solar Dynamics Observatory has captured high-resolution images of coronal loops undergoing rapid brightening events that correlate with no obvious surface activity. These mysterious energy releases occur in regions where magnetic field lines should remain stable, suggesting that our understanding of coronal heating mechanisms may be fundamentally incomplete. Into this already unstable electromagnetic environment comes 3I Atlas, carrying metallic compounds that could provide catalytic pathways for energy release processes we've never observed before. Consider the cascade of interactions that could unfold as exotic chemistry from interstellar space encounters the sun's magnetic architecture. The comet's nucleus contains ratios of metallic elements that reflect formation conditions unlike anything in our solar system. When these materials begin sublimating under intense solar heating, they'll create clouds of charged particles with electrical properties that have no precedent in space physics literature. The Parker Solar Probe's recent passes through the solar corona have revealed that the plasma environment near our star operates according to principles that challenge theoretical predictions. Magnetic field reversals occur on timescales measured in seconds, rather than the hours or days that models suggest. Particle acceleration events generate energies that approach cosmic ray levels. Most mysteriously, the probe has detected coherent electromagnetic waves propagating through the corona at frequencies that don't match any known plasma oscillation modes. These observations suggest that the Sun's magnetic field exists in a state of barely controlled chaos, maintained in dynamic equilibrium through processes we don't fully understand. The introduction of foreign chemistry from 3I Atlas could destabilize this delicate balance by providing new pathways for electrical current flow, or by seeding magnetic reconnection events in regions that normally remain magnetically quiet. The timing of this encounter coincides with what solar physicists call a magnetic flux emergence event, currently developing on the Sun's eastern limb. Satellite observations show a massive magnetic structure rising through the photosphere, carrying field strengths that exceed typical sunspot values by significant margins. If this emerging flux region becomes unstable during 3I Atlas's perihelion passage, the combination could trigger electromagnetic disturbances that propagate throughout the entire heliosphere. The physics governing magnetic reconnection in stellar environments involves energy densities that push matter into exotic states rarely encountered elsewhere in the universe. When magnetic field lines snap back into lower energy configurations, the process accelerates particles to relativistic velocities and generates electromagnetic radiation, spanning the entire spectrum from radio waves through gamma rays. The energy release occurs so rapidly that causality itself becomes a limiting factor in how quickly the disturbance can propagate through surrounding plasma. Under normal solar conditions, these reconnection events follow predictable patterns driven by the internal dynamics of magnetic flux tubes rising through the convection zone. But the presence of foreign metallic particles could alter the plasma conductivity in ways that change the fundamental physics of how reconnection proceeds. Enhanced conductivity might allow magnetic field lines to maintain higher stress levels before snapping, leading to more energetic releases when reconnection finally occurs. The European Space Agency's Solar Orbiter mission has positioned itself to observe 3I Atlas from a vantage point that will provide stereo imaging of any electromagnetic disturbances that develop during perihelion passage. The spacecraft's suite of instruments includes magnetometers sensitive enough to detect field variations caused by the comet's passage, particle analyzers capable of identifying exotic chemical species in the solar wind, and imaging systems that can capture plasma dynamics across multiple wavelengths simultaneously. Ground-based solar observatories have coordinated their observation schedules to provide continuous monitoring throughout the critical encounter period. The Swedish Solar Telescope, operating from the Canary Islands with adaptive optics that correct for atmospheric turbulence, will capture magnetic field maps of the Sun's surface with resolution fine enough to detect localized disturbances that might correlate with the comet's electromagnetic influence. The Big Bear Solar Observatory in California has installed new instrumentation specifically designed to monitor rapid changes in coronal magnetic field configurations. Their vector magnetograph can measure field strength and direction across the Sun's disk every few seconds, providing real-time detection of any anomalous magnetic activity that develops during 3I Atlas's closest approach. Radio observatories worldwide stand ready to detect the electromagnetic signatures of enhanced particle acceleration should magnetic reconnection events occur during the comet's solar encounter. The Very Large Array in New Mexico has dedicated observation time to monitor solar radio emissions at frequencies that could reveal particle populations accelerated by comet-triggered electromagnetic processes. The Atacama Large Millimeter Array has developed specialized observation protocols for detecting the millimeter wave signatures of hot plasma that could result from enhanced magnetic activity. These wavelengths provide unique insights into the temperature and density structure of coronal material that might be disturbed by interactions with interstellar chemistry. International coordination among space weather monitoring centers has established communication protocols for rapid dissemination of any unusual electromagnetic activity detected during the perihelion passage. The Space Weather Prediction Center in Boulder, Colorado, will serve as the central hub for integrating observations from multiple spacecraft and ground-based facilities into coherent assessments of potential technological impacts. The challenge lies in distinguishing between natural solar variability and genuine comet-induced effects when analyzing the flood of observational data that will flow from instruments throughout the solar system. Advanced machine learning algorithms are being trained on historical solar data to recognize patterns that might indicate external influences on our star's electromagnetic behavior. Statistical analysis techniques developed for detecting subtle signals in noisy astronomical data will be applied to search for correlations between the comet's position and any electromagnetic anomalies that develop in the solar environment. The analysis must account for the complex propagation delays as electromagnetic disturbances travel from their generation sites near the Sun outward through interplanetary space. The implications extend far beyond immediate space weather concerns into fundamental questions about how stellar systems interact with the interstellar medium that surrounds them. If 3I Atlas can indeed influence our Sun's electromagnetic behavior, similar processes must occur throughout the galaxy as interstellar objects encounter various stellar environments during their cosmic wanderings. These interactions could represent a previously unrecognized coupling mechanism that links stellar magnetism across vast distances. Interstellar visitors might serve as carriers of electromagnetic information, transporting magnetic field signatures and plasma properties between stellar systems separated by light years of empty space. Understanding these processes could illuminate aspects of galactic evolution that remain completely invisible through conventional astronomical observation techniques. The chemical inventory preserved within 3I Atlas provides direct samples of matter processed under stellar conditions that may have differed dramatically from those in our local solar neighborhood. The isotopic ratios locked within the comet's nucleus record nuclear fusion processes that operated in stellar cores with different masses, temperatures, and chemical compositions than our Sun. When this ancient chemistry encounters our Sun's contemporary magnetism, the interaction represents more than just a local electromagnetic phenomenon. It becomes a collision between different epochs of cosmic evolution, a meeting of materials formed under primordial stellar conditions with electromagnetic processes operating in our modern solar environment. The preservation mechanisms that allowed complex metallic compounds to survive billion-year journeys through the radiation and temperature extremes of interstellar space remain one of the most profound mysteries surrounding 3I Atlas. The demonstrated survival of delicate chemical signatures suggests either extraordinary protection mechanisms or molecular architectures more robust than anything formed under solar system conditions. Laboratory experiments attempting to simulate the preservation of metallic compounds under interstellar conditions face insurmountable technical challenges. No terrestrial facility can replicate the combination of cosmic ray bombardment, temperature cycling, and electromagnetic field exposure that characterizes the interstellar environment over geological timescales. Computer simulations provide limited insights because they depend on assumptions about material properties and degradation mechanisms that remain largely untested by direct observation. The chemical analysis of 3I Atlas during its solar encounter will provide the first definitive measurements of how interstellar processing affects matter over cosmic time periods. The dust production patterns during perihelion heating could reveal whether different regions of the nucleus carry distinct chemical signatures reflecting the heterogeneous conditions under which the comet originally formed. If 3I Atlas accreted materials from different zones within its birth stellar system, various portions of its surface might sublimate unique combinations of exotic compounds when exposed to solar radiation. These compositional variations would create time-variable electromagnetic effects as the comet rotates, producing modulated disturbances in the solar wind and magnetic field environment. Such temporal signatures would provide additional tools for distinguishing comet-induced effects from the background noise of natural solar variability. The rotation period of 3I Atlas remains poorly constrained due to observational challenges associated with its great distance from Earth and relatively small size. Preliminary estimates suggest a rotation period of several hours, but precise determination requires extended photometric monitoring campaigns that span multiple rotational cycles. The orientation of the rotation axis relative to the comet's orbital plane could influence how electromagnetic interactions develop during perihelion passage. If the axis alignment exposes different hemispheres to peak solar heating at different times, the resulting sublimation patterns might create asymmetric distributions of charged particles that evolve as the comet tumbles through space. Ground-based radar observations have attempted to characterize the nucleus shape and surface properties, but the results remain ambiguous due to signal strength limitations at interplanetary distances. The Arecibo Observatory's collapse in 2020 eliminated one of the most powerful planetary radar systems, reducing our capability to study small solar system objects through radio techniques. The Goldstone Deep Space Communications Complex in California continues radar observations of 3I Atlas using its 70-meter antenna, but the echo strength decreases rapidly as the comet approaches the Sun and becomes increasingly difficult to separate from solar radio interference. Space-based radar systems could potentially provide better characterization of the nucleus properties, but no current missions carry the specialized equipment needed for high-resolution radar mapping of distant objects. Future interstellar visitor investigations might benefit from dedicated radar satellites positioned at strategic locations throughout the solar system. The spectroscopic evolution of 3I Atlas's coma during solar approach provides real-time observations of how exotic interstellar chemistry responds to increasing thermal energy input. Different molecular species begin sublimating at characteristic temperatures, creating a sequential revelation of the nucleus's chemical stratification. The carbon dioxide dominance already detected suggests that the comet's volatile inventory differs fundamentally from typical solar system specimens. As perihelion heating penetrates deeper into the nucleus, additional chemical surprises may emerge from subsurface layers that have remained frozen since the object's formation billions of years ago. The James Webb Space Telescope's infrared capabilities could detect molecular emission lines from trace species that remain below the sensitivity thresholds of ground-based instruments. Complex organic molecules, if present, might become detectable only during the peak heating phase when sublimation rates reach their maximum values. The spatial distribution of different chemical species within the coma reveals information about their origins within the nucleus and their subsequent behavior after sublimation. The unusual forward-pointing glow observed in early images suggests dust dynamics, unlike those seen in conventional comets, possibly indicating grain populations with exotic optical or electromagnetic properties. The interaction between sublimating gases and dust particles creates the visible phenomena that make comets spectacular objects for both scientific study and public observation. But in the case of 3I Atlas, these interactions might also generate electromagnetic effects that remain completely invisible to optical telescopes, while potentially influencing the Sun's magnetic field behavior. Charged dust grains become coupled to magnetic field lines and can be accelerated to high velocities by electric fields in the solar wind plasma. If 3I Atlas produces unusually large quantities of electrically active dust, these particles could propagate throughout the inner solar system and create space weather effects that persist long after the comet itself has departed. The size distribution of dust particles released during sublimation depends on the physical properties of the nucleus material and the violence of the outgassing process. Interstellar processing over billion-year timescales might have created surface layers with unusual mechanical properties that fracture differently than typical solar system materials when heated. Microscopic analysis of dust particles captured by spacecraft or collected in Earth's atmosphere could provide direct evidence of interstellar processing mechanisms and chemical environments that operated around the comet's birth star. However, the logistics of sample collection from 3I Atlas present enormous technical challenges given its high velocity and unfavorable trajectory. The Stardust mission successfully collected samples from Comet Wild 2 using aerogel capture techniques. But that encounter occurred at much lower relative velocities than would characterize any potential rendezvous with 3I Atlas. The energy scales involved in high-speed dust impacts could vaporize sample materials before they could be analyzed. Alternative sampling strategies might involve flying through the comet's dust trail at carefully chosen locations where particle densities remain high, but encounter velocities stayable ranges within management. Such missions would require precise navigation and timing that pushes spacecraft guidance systems to their operational limits. The electromagnetic environment through which 3I Atlas travels during its solar encounter represents the most extreme plasma physics laboratory accessible to human observation. Magnetic field strengths approach values that challenge the stability of atomic matter itself. Particle energies rival those produced in the most powerful terrestrial accelerators. Temperature gradients span ranges from near absolute zero to stellar interior conditions, within distances measured in planetary diameters. Understanding how interstellar chemistry behaves under these extreme conditions could provide insights into fundamental physics processes that operate throughout the universe. The data collected during 3I Atlas's perihelion passage will likely influence theoretical frameworks across multiple scientific disciplines for decades to come. The countdown to this unprecedented encounter continues as ancient chemistry from the space between stars approaches its confrontation with the electromagnetic fury surrounding our Sun. Whether the result proves scientifically revolutionary or practically disruptive, humanity stands witness to cosmic processes that connect our local stellar environment to the vast networks of matter and energy flowing throughout our galaxy. The resolution of this celestial drama will illuminate not just the nature of one enigmatic visitor, but fundamental aspects of how the universe operates on scales that dwarf terrestrial experience, while potentially affecting the technological civilization we've built in our small corner of cosmic space. The electromagnetic cascade that might unfold during these critical hours defies simple explanation. Picture the Sun's magnetic field as an invisible web stretching across millions of kilometers, each strand vibrating with energies that could power entire civilizations. Now imagine dropping something completely foreign into this delicate architecture, something that carries chemical signatures from a stellar environment so alien that our periodic table barely recognizes the elemental ratios preserved within its ancient nucleus. The interaction zones where 3I Atlas will soon find itself represent regions where physics operates at the absolute limits of natural law. Here, magnetic field lines stretch until they reach their breaking point, snapping back with violence that accelerates particles to significant fractions of light speed. The plasma temperatures in these zones exceed those found in stellar cores, creating conditions where atoms themselves become unstable and matter exists in states that challenge our understanding of fundamental forces. What makes this encounter particularly dangerous is the way magnetic energy accumulates in the Sun's corona through processes we're only beginning to understand. Like a vast electrical capacitor storing charge across space-sized distances, the coronal magnetic field builds up energy reservoirs that can discharge catastrophically when the right triggering mechanism appears. 3I Atlas, with its exotic metallic chemistry and unprecedented mass, might provide exactly such a trigger. The sequence of events that could unfold follows a terrifying logic that space physicists have modeled but never observed in reality. As the comet's unusual chemistry begins sublimating under extreme solar heating, it creates clouds of charged particles with electrical properties unlike anything naturally occurring in our solar system. These particles follow magnetic field lines like invisible highways. accumulating in regions where field configurations become unstable. The critical moment arrives when magnetic stress exceeds the breaking point. Field lines that have been twisted into impossible geometries by solar convection suddenly snap back towards simpler configurations, releasing energy equivalent to millions of nuclear weapons in microseconds. But here's where 3I Atlas changes everything. The foreign metallic particles provide new pathways for electrical current flow, potentially allowing field lines to maintain higher stress levels before breaking, leading to even more catastrophic energy releases. Recent observations from the Parker Solar Probe have revealed that magnetic reconnection events in the solar corona occur far more frequently and violently than theoretical models predicted. The spacecraft has detected particle acceleration episodes that generate energies approaching cosmic ray levels, suggesting that our Sun's magnetic field exists in a state of barely controlled chaos. The introduction of exotic interstellar chemistry into this unstable system could push it beyond the point of dynamic equilibrium. The propagation effects of such disturbances follow the inexorable laws of electromagnetic physics. Initial disturbances generated near the Sun travel outward at light speed, potentially triggering secondary reconnection events throughout the solar system's magnetic architecture. These cascading failures could create electromagnetic storms that persist for weeks or months, far exceeding anything in the historical record of space weather events. The technological vulnerabilities of our interconnected civilization become starkly apparent when confronted with such possibilities. Satellite constellations that provide GPS navigation, internet connectivity, and weather monitoring operate in radiation environments that could become lethal during severe electromagnetic storms. The simultaneous failure of multiple satellite systems would cripple communications networks just when they're needed most to coordinate emergency responses. Power transmission more immediatids face even threats from geomagnetically induced currents that could flow through high-voltage lines spanning continental distances. These currents, generated when changing magnetic fields induce electrical flows in large conductors, have the potential to overload transformers and trigger cascading blackouts that might persist for months, while replacement equipment is manufactured and installed. The economic modeling of such scenarios produces projections that challenge our ability to comprehend disaster on scales. Loisuch that Ads of London estimates severe space, global economic damages weather event could cause exceeding $2 trillion, primarily through the destruction of electronic infrastructure and the cascading effects of prolonged electrical outages. These calculations assume disturbances within the range of historical experience, but 3I Atlas introduces variables that push far beyond conventional risk assessment boundaries. Aviation particularly systems present acute vulnerabilities during electromagnetic disturbances. Commercial aircraft depend on GPS navigation systems that become unreliable during geomagnetic storms. High-frequency radio communications, essential for flights over polar regions, can be completely disabled by solar radio interference. Most concerning, the increased radiation exposure at cruising altitudes during severe space weather events could pose direct health risks to passengers and flight crews on intercontinental routes. Medical facilities face their own electromagnetic vulnerabilities through dependence on sensitive electronic equipment that could malfunction during severe space weather events. Magnetic resonance imaging systems, computerized tomography scanners, and electronic patient monitoring devices operate near their electromagnetic tolerance limits under normal conditions. Enhanced electromagnetic interference could render these life-saving technologies temporarily inoperable precisely when they might be needed most. The financial implications extend beyond immediate infrastructure damage into long-term economic disruption, caused by the collapse of just-in-time supply chains that depend on precise coordination through electronic communications. Modern commerce relies on satellite-based tracking systems, electronic payment networks, and computerized inventory management that could fail simultaneously during severe electromagnetic events. Yet these terrestrial concerns represent only the most immediate annable consequences, of what might unfold during 3I Atlas's solar encounter. The scientific implications stretch into fundamental questions about how matter and energy behave under conditions impossible to replicate in any terrestrial laboratory. The data collected during this unprecedented interaction could revolutionize our understanding of plasma physics, magnetic field dynamics, and the electromagnetic processes that govern stellar evolution throughout the universe. The observational campaign preparing for perihelion passage represents the most comprehensive space weather monitoring effort ever attempted. Instruments aboard dozens of spacecraft and at observatories worldwide will capture electromagnetic signatures across every wavelength from radio waves through gamma rays. Advanced computer algorithms will attempt to distinguish between natural solar variability and genuine comet-induced effects in real-time data streams flowing from throughout the solar system. The Parker Solar Probe stands uniquely positioned to observe electromagnetic interactions from within the Sun's corona itself. This remarkable spacecraft operates in an environment where plasma temperatures exceed 1 million degrees, while radiation levels would instantly destroy conventional electronics. Its heat shield maintains instrument temperatures near room conditions, while the surrounding space writhes with electromagnetic violence that dwarfs any terrestrial phenomenon. The probe's magnetometers can detect field variations smaller than 1 part in a million of Earth's magnetic field strength, potentially revealing subtle electromagnetic signatures associated with 3I Atlas that would remain invisible to more completely distant observers. Its particle analyzers can identify individual atomic species in the solar wind, possibly detecting the exotic chemistry sublimating from the comet's nucleus as it approaches perihelion. Ground-based solar observatories have coordinated observation schedules to provide continuous monitoring throughout the critical encounter period. The Daniel K. Inouye Solar Telescope in Hawaii will capture magnetic field maps across the Sun's surface, with resolution fine enough to detect localized disturbances that might correlate with the comet's electromagnetic influence. The Swedish Solar Telescope will contribute high-cadence observations that could reveal rapid changes in coronal magnetic field configurations. Radio observatories worldwide stand ready to detect the electromagnetic signatures of enhanced particle acceleration should magnetic reconnection events occur during the solar encounter. The Very Large Array has dedicated observation time to monitor solar radio emissions at frequencies that could reveal particle populations accelerated by comet-triggered electromagnetic processes. These radio signatures would provide some of the first definitive evidence that interactions are occurring between interstellar chemistry and solar magnetism. The European Solar Orbiter mission provides additional vantage points from its elliptical trajectory that carries it closer to the Sun than most previous space missions. Its instruments will monitor solar wind properties, energetic particle populations, and magnetic field configurations from perspectives unavailable to Earth-based observers. The combination of Parker Solar Probe and Solar Orbiter observations could provide stereo imaging of any electromagnetic disturbances that develop. Space-based X-ray and extreme ultraviolet telescopes will watch for the high-energy signatures of magnetic reconnection events should they occur during perihelion passage. These wavelengths reveal the hottest plasma in the solar corona, where magnetic energy gets converted into particle acceleration and electromagnetic radiation. Any enhancement during in these emissions, 3I Atlas's closest approach would provide smoking gun evidence of interaction between interstellar matter and stellar magnetism. The coordination challenges in this involve global observation campaign reflect the unprecedented nature of the scientific opportunity. Never before have we possessed both the instrumental capabilities and the advance warning necessary to study how truly exotic interstellar chemistry behaves when subjected to stellar-strength electromagnetic fields. The lessons learned could influence space weather prediction models for generations to come. The theoretical frameworks attempting to predict interaction outcomes span a remarkable range of possibilities, from complete electromagnetic silence to cascading solar storms that could affect planetary magnetospheres throughout the solar system. The uncertainty reflects fundamental gaps in our understanding of how exotic materials behave under the extreme conditions found near stellar surfaces. Computer simulations provide limited guidance because they depend on assumptions about material properties and interaction mechanisms that remain largely untested by observation. Laboratory experiments face insurmountable technical challenges in replicating the combination of magnetic field strengths, plasma temperatures, and radiation environments found in the solar corona. The historical record offers little precedent because previous comets that approached the Sun carried familiar solar system chemistry, formed under conditions similar to those in our local stellar neighborhood. Even spectacular encounters like Comet Ison's Solarzing involve grad materials with compositions well within the range of solar system experience. 3I Atlas represents humanity's first opportunity to observe how genuinely alien chemistry responds to stellar electromagnetic environments. The chemical inventory preserved within this ancient wanderer tells a story spanning billions of years of cosmic evolution. The isotopic ratios locked in its nucleus record nuclear processes that operated in stellar cores fundamentally different from our Sun. The elemental abundances reflect formation environments where different fusion reactions dominated energy production. The molecular structures preserve information about temperatures, pressures, and magnetic fields alien that characterize stellar systems during earlier epochs of galactic history. When this ancient chemistry encounters our Sun's contemporary magnetism, the collision represents more than just a local space weather event. It becomes a meeting between different chapters of cosmic evolution, a confrontation between matter formed under primordial stellar conditions and electromagnetic processes operating in our modern solar environment. The preservation mechanisms that allowed complex metallic compounds to survive interstellar transport over geological timescales remain among the most profound mysteries in contemporary astronomy. The demonstrated survival of delicate chemical signatures suggests either extraordinary protection processes or molecular architectures more robust than anything formed under local solar system conditions. The electromagnetic environment through which 3I Atlas traveled during its billion-year journey included magnetic fields much weaker than those near stars, but cosmic ray particles following these field lines could have gradually modified the comet's internal structure through radiation processing mechanisms. If the object RESI carries dual magnetization from its interstellar wandering, that embedded magnetic field could interact directly with solar magnetism in ways that remain purely theoretical. The rotation characteristics of 3I Atlas add geometric complexity to potential electromagnetic interactions. As the comet tumbles through space, different portions of its surface become exposed to solar heating and magnetic field lines. The resulting sublimation patterns could create asymmetric distributions of charged particles that influence how electromagnetic disturbances propagate through the surrounding plasma environment. The dust production patterns during solar heating present another pathway for electromagnetic interaction. As volatile ices sublimate from the nucleus surface, they carry microscopic particles that become electrically charged through various mechanisms. These charged grains follow complex trajectories determined by electromagnetic forces, gravitational attraction, and radiation pressure from sunlight. The size distribution and composition of dust particles released by 3I Atlas could differ dramatically from typical solar system comet debris. Interstellar processing mechanisms operating over cosmic timescales might have created grain populations with unusual electrical conductivities or magnetic susceptibilities that influence their behavior in the Sun's electromagnetic environment. Large dust grains follow ballistic trajectories largely unaffected by electromagnetic forces, but smaller particles become coupled to magnetic field lines and can be accelerated to high velocities by electric fields in the solar wind plasma. If 3I Atlas produces unusually high proportions of electrically active small dust, these particles could propagate throughout the inner solar system and influence space weather conditions near Earth long after the comet itself has departed. The spectroscopic signatures of sublimating exotic chemistry will provide real-time observations of how interstellar materials respond to stellar heating. Different molecular species begin outgassing at characteristic temperatures, creating sequential revelation of the nucleus's chemical stratification, as solar energy penetrates deeper into frozen layers that have remained unchanged since the object's formation. The carbon dioxide dominance already detected suggests fundamental differences from typical solar system volatile inventories. As perihelion heating intensifies, additional chemical surprises may emerge from subsurface regions that preserve even more exotic compounds formed under conditions impossible in our local stellar environment. The James Webb Space Telescope's unprecedented infrared sensitivity could detect molecular emission lines from trace species that remain below detection thresholds for ground-based instruments. Complex organic molecules, metallic compounds, and exotic ice phases might become observable only during peak heating when sublimation rates reach maximum intensity. The spatial distribution of different chemical species within the expanding coma reveals information about their origins within the nucleus and their behavior after sublimation. The unusual forward-pointing glow observed in early images suggests particle dynamics unlike those in conventional comets, possibly indicating interactions between exotic chemistry and electromagnetic fields that create previously unknown phenomena. The magnetic field measurements during perihelion passage will provide crucial tests of theoretical predictions about electromagnetic coupling between interstellar matter and stellar magnetism. If 3I Atlas carries embedded magnetic fields from its journey through interstellar space, those fields might become detectable as the comet approaches regions where solar magnetism becomes intense enough to interact with weaker external fields. The energy scales involved in potential magnetic reconnection events triggered by exotic interstellar chemistry dwarf anything in human experience. A single reconnection episode can release energy equivalent to millions of nuclear weapons in microseconds, accelerating particles to significant fractions of light speed while generating electromagnetic radiation across the entire spectrum from radio waves through gamma rays. If the comet's passage triggers multiple simultaneous reconnection events throughout the Sun's magnetic architecture, the cumulative energy release could exceed anything observed during the space age. Such an electromagnetic storm would propagate the solar system at throughout light speed, potentially overwhelming planetary magnetospheres and creating radiation environments hostile to both technological systems and biological organisms. The probability assessments for such extreme outcomes remain highly speculative because the unprecedented nature of 3I Atlas makes risk evaluation extraordinarily difficult. The combination of unusual mass, exotic chemistry, and mysterious origins places this object outside the experience base that informs current space weather prediction models. Conservative estimates suggest that electromagnetic disturbances will likely fall within ranges of natural solar variability, causing minimal disruption while providing valuable scientific data about stellar-interstellar interactions. More aggressive projections warn of cascading electromagnetic failures that could temporarily disable global communication networks and force implementation of emergency protocols designed for extreme space weather scenarios. The uncertainty itself drives both scientific fascination and practical concern as humanity confronts the possibility of witnessing cosmic-scale electromagnetic phenomena while remaining vulnerable to their technological consequences. The intersection of astronomical discovery with infrastructure risk management creates tensions between curiosity and caution that will persist throughout the co-encounter.met's solar. As this ancient messenger approaches its appointment with electromagnetic fire, the countdown continues toward what might become either humanity's most comprehensive documentation of interstellar visitor behavior or our first direct observation of how exotic chemistry can trigger stellar magnetic storms. The resolution will illuminate fundamental aspects of cosmic connectivity, while testing our technological civilization's resilience against forces operating on galactic scales. The data streams flowing from instruments throughout the solar system during the coming days will capture more than measurements of a single astronomical event. They represent evidence of processes that link stellar systems across vast distances, demonstrate how matter and energy flow through cosmic ecosystems, and provide tests of physical theories under conditions beyond terrestrial replication. The electromagnetic drama about to unfold connects our local stellar environment to networks of matter and magnetism operating throughout the galaxy, reminding us that even in our technological sophistication, we remain subject to cosmic forces that dwarf human comprehension while shaping the very foundations of the universe we call home. The mathematical precision required to predict electromagnetic outcomes during 3I Atlas's solar encounter pushes computational modeling beyond its current limits. Supercomputers running plasma physics simulations must account for millions of variables operating across spatial scales spanning kilometers to astronomical units. Temperature gradients that transition from interplanetary cold to stellar interior heat within planetary diameters. Magnetic field strengths that fluctuate by orders of magnitude across distances smaller than terrestrial cities. Each computational cell in these models represents volumes of space larger than entire nations, yet the physics demands resolution fine enough to capture individual particle interactions that could cascade into system-wide electromagnetic disturbances. The processing requirements exceed the capabilities of most national computing centers, forcing researchers to make approximations that introduce uncertainties into already speculative predictions. The fundamental challenge lies in modeling how exotic interstellar chemistry behaves when subjected to conditions that exist nowhere else in the known universe except near stellar surfaces. Laboratory experiments attempting to simulate these interactions face insurmountable technical barriers. No terrestrial facility can simultaneously reproduce million-degree temperatures, magnetic field strengths measured in thousands of Gauss, and particle densities that approach solid matter compressed into plasma states. Wind tunnel testing revolutionized aerospace engineering by allowing controlled study of airflow over aircraft surfaces, but there exists no equivalent facility for studying how sublimating metallic compounds interact with stellar magnetic fields. The physics operates in regimes where quantum mechanics, relativistic effects, and classical electromagnetism all contribute simultaneously to phenomena that challenge theoretical understanding, even under controlled conditions. The observational data streaming back from Parker Solar Probe reveals that our theoretical frameworks may be fundamentally incomplete. The spacecraft has detected magnetic field reversals occurring on timescales measured in seconds rather than the hours that models predict. Particle acceleration events generate energy spectra that don't match any known plasma physics mechanism. Most mysteriously, coherent electromagnetic waves propagate through the corona at frequencies that correspond to no theoretical plasma resonance modes. These discoveries suggest that stellar magnetism operates through processes we haven't identified, much less understood well enough to predict how they might respond to external perturbations. The introduction of foreign chemistry from 3I Atlas into this already mysterious environment could trigger phenomena that existing theories cannot anticipate or explain. As 3I Atlas continues its ancient dance toward perihelion, carrying within its frozen nucleus the chemical secrets of stellar environments we can never visit, we find ourselves standing at the threshold of discovery. Whether this cosmic messenger triggers electromagnetic storms that reshape our understanding of solar physics, or passes quietly through its closest approach, while revealing only the subtle signatures of exotic interstellar chemistry. Its journey has already transformed how we perceive our place in the galactic ecosystem. The data flowing from telescopes and spacecraft worldwide captures more than the properties of a single visitor from the space between stars. It documents our species' growing ability to witness cosmic processes that connect stellar systems across vast distances and geological timescales, reminding us that even in our technological sophistication, we remain both observers and participants in the electromagnetic symphony that governs our corner of the universe.